Thank you very much. And first, I really thank the organizers for giving me a chance to visit here and give an opportunity to give this talk. This is a very nice conference indeed. So this is on Bloch algebra, Hecke algebra, classical type, and so let us start with definition of Hecke algebra. Probably many in this audience know the definition. So, but let me repeat. So let K be an algebraic closed field of odd characteristics. We assume odd characteristic here, and we fix Q, which is not equal to 1. So Q is equal to 1 is excluded for simplicity, and consider the Hecke algebra HWQ associated with the reducible Weyl group W. And so it has braided relations of type A or type B, and quadratic relations for the equal parameter case is this, Ts minus Q times Ts plus 1 equals 0 for all Coxeter generator S. And in 2007, Hecke published a paper in Inventiones, and that is a very surprising result that if P is not 2 equals or 3 for WE6 and WE7 and WF4 and WG2, and if further P is not equal to 5 for WE8, then Hecke algebra is, and this Bloch algebra is a cellular algebras. So amazingly, so for type A and type B it was known, but amazingly all the other fine Hecke algebra cellular if parameters are equal. And in this talk we focus on classical types ABD, and for type D we consider the unequal parameter case as well. So let capital Q be another non-zero parameter, and we have then additional generator T0. To T0 is I'd better write the Coxeter diagram. So T0 is a generator for here, and this is a generator for Coxeter diagram. And for T0, the quadratic relation is T0 minus capital Q times T0 plus 1 is 0. And now I would like to say something about representation type of Bloch algebra, Hecke algebra. So I start with parameterization blocks. And in type A, it is a classical result. So let A be the quantum characteristics. And since we assume Q is not equal to 1, this is just the multiplicative order of Q in the field K. And if type is n minus 1, that is, if W is a symmetric group on n letters, then blocks of Hecke algebras are labeled by equal partitions, kappa with weight of this form. So n minus the size of kappa should be divisible by E. And then, so as is already well known to the expert, we may view this result as follows. So we consider cut-Moody algebra associated to A1 E minus 1. Here E is a quantum characteristic. And say, I would like to say something here. Recently some people use E instead of E minus 1 here. But then E plus 1 becomes a quantum characteristic. And I prefer E to be the quantum characteristics. So please write like this. And if you don't like to write E minus 1, please use SLE hat, please. And now, and then, no, which direction should I go? No. Yes. Here, yes, thank you. So then we consider its weight lattice P, and consider the basic representation V lambda 0. where, so, 0 is the node added to the finite thinking diagram to obtain the affine diagram A1, E minus 1. And the lambda 0 is the fundamental weight attached to this node. So then we have a weight decomposition like this. And then V lambda 0 is realized on the vector space with basis consisting of elastic partitions, and the leveling set for the blocks may be interpreted as this set of weights. So the weights which appear in V lambda 0 such that height of this difference is equal to n. And so height is, so by definition, the sum of coefficients of simple roots when we write this other nonlinear, non-negative interior combination of simple roots. And so it already appeared Khrushchev talk. So so we write, mu as kappa minus weight of kappa delta, where delta is the null root, and kappa is a weight in the orbit through the highest weight. And so if we realize V lambda 0 on the vector space with base consists of elastic partitions, then the weight space V lambda 0 kappa is one-dimensional, and it consists of the equal. So this weight uniquely defines the equal, and so this matches with the classical abacus notations. So this is the type A classification for blocks, and then for block Hecke type B, first we consider two parameter case, so H and QQ. So and generators are like this, T0, T1 to Tn minus 1, and the quadratic relation are like this. And so for T0 and T1 we have type B Bray relation, and for the other adjacent generators we have the ordinary Bray relations. And if they are not directly connected, then they commute. And then a very old result by different James says that if minus capital Q is not a parallel Q, then this Hecke algebra is Morita equivalent to direct sums of tensor product of two Hecke algebra associated with symmetric group on characters and symmetric group on n minus characters. So so blocks appears here. So that tensor product two blocks. So basically, so it says that blocks of H and QQ when minus capital Q is not the power Q are labeled by pairs of equals by the previous result, or we can say in terms of weights, mu and nu, such that mu appears as a weight of V lambda 0, and nu appears as a weight of V lambda 0, and the sum of height is n. So this is the case for minus capital Q is not the power of Q. And when minus capital Q is a power of Q, say Q to S, where S is between 0 to and n e minus 1, then by the result by Lyra Mathas, who proved the result for more general cyclotomic Hecke algebras, says that the blocks of Hecke algebra are labeled by weight mu, such that mu appears as a weight of V, highest weight modulo V lambda 0 plus lambda s, and the height of this is equal to n. So this is the parameterization of blocks in type P, and for type D, we consider the case where capital Q is 1 first. Then it has two commuting evolutions, sigma and tau. Sigma sends T0 to minus T0, and Ti to Ti for I not equal to 0. The tau sends T1 to T0, T1, T0, and Ti to Ti for I not equal to 1. Then this Hecke of type D is a fixed point algebra of sigma, and for block B, capital B of H and Q1, we have either the fixed point algebra B is a single block small b of HWQ, or B sigma is the direct sum of two blocks B prime and B double prime of HWQ. And this is a standard, this is by standard argument on covers of blocks and Clifford theory, basically. So we have B is fixed by this automorphism in case 1, and tau swaps B prime and B double prime in case 2. And in the first case, we say that capital B covers B, and the second case, we say that capital B covers two blocks B prime and B double prime. So we have explained the parameterization blocks, and now I'm going to explain representative type, which probably the audience also know well. But representative type is a concept to tell the possibility of classifying in the composite objects. So you know it already appeared probably Chan Chan's talk. So if there are only finitely many in the composite A modules up to isomorphism, then we say that A is finite, and otherwise A has infinite representation type, and there is a precise definition for term representation type here. And if I say term, it means infinite term. So we exclude finite type from here. And so basically it says that for each dimension D, there are finitely many one-dimensional family such that they cover all the indecomposable of that dimension, except for finitely many. And then we have the notion of wildness, and so this is the standard thing. So we have some module over non-commutative polynomial ring in two variables, and then we have some embedding of indecomposables from this algebra to A, and probably you know them well. And so the famous trigonometry theorem says that over algebra field, every finite dimensional algebra has finite, infinite term, or wild representative type, and these types are mutually exclusive. And the well-known examples are, for example, if A is a fast algebra of a cyclic quiver, and if K is a finite thinking, then A is finite representation type, and if Q is a affine type, then A has infinite term representation type. And another example is a block algebra, a group algebra of finite group, and they are determined by the defect group, by bond-length laws for term type. And for finite type, it is a cyclic case. So now I would like to introduce Bauer tree algebras. The name Bauer tree algebra also appeared in previous talks today. And so I would like to explain a little. So let G be a finite graph. So V is a set of vertices, and E is a set of undirected edges. So this is an undirected graph. And we assume that there are no loops and no multiple edges. And it is called tree if the number of vertices is 1 greater than the number of edges. This is the standard definition in graph theory. And a Bauer tree is a tree with the following additional data. So for each vertex, a cyclic ordering is given on the set of edges which has V as an endpoint. And there is at most one vertex which is assigned an integer m which is greater than 1. And the vertex from 2 is called the sectional vertex, and integer m is called its multiplicity. And there is a standard definition which defines a class of symmetric algebras called Bauer graph. Sorry, maybe so Bauer tree, each Bauer tree. So of course there is a notion of Bauer graph algebra. Here only you consider Bauer tree. So there's a standard way to define a class of algebras, and so symmetric Bauer tree algebras. and where simple modules are labeled by the edges, and the data 1 and 2 determine the logical seeds of indecomposable modules. And this defines uniquely a basic algebra and the class of multi-equivalent class of symmetric algebras. And here, we are only interested in the special case that the Brauer tree is a straight line with n edges and without exception vertex. So in this case, we know as Brauer tree is a very familiar one. So if n is greater than 1, then so the first pim is a unishare with this logical seeds, and the second one is like this, and so on. And the last one is also unishare. That's one. The first one is unishare. And so this is a Brauer tree as for straight line without exception vertex. So now I write. So here I write these in these things. I write these things here, and then I write to today state this as the main cell. It is actually a corollary of another cell, right? So what is the main result? So I write to state. So let it be a block algebra, Hecke algebra, classical type 1 algebra closed field of odd characteristic. And if V is finite, then it is a Brauer tree algebra whose Brauer tree is a straight line without excess vertex. And the proof starts with determining the type of Hecke algebra, classical type blockwise, which I'm going to explain. And this is actually the main result. So representation type in type A were already known years ago. So it was the result by Erdmann Nakano in 2002. So suppose that W is the symmetric group and B kappa be the block labeled by an equal kappa. Then the block is simple algebra if weight is 0, and not simple but the finite if and only if weight is 1, and the infinite term if and only if equal to, and the weight kappa is 2, and while otherwise. And further, if B kappa has a finite type, then it is a Brauer tree algebra whose tree is a straight line without exception vertex. This computation was already made by Uno around 1990. And for type D, we reduce the question to type B. This is the proposition. Suppose that W is a Weyl group of type D, and B is a block of the Hecke algebra. If B is covered by a block capital B of H and Q1, then B and small b and capital B have the same representation type. And so it is stated in a paper published this year, but proof is not at all difficult. So basically, what we have to consider are the case where Hecke algebra is type B. Okay. So now we concentrate on the case where Hecke algebra is of type B. And we first consider a case that the minus capital Q is not part of Q. And then, as I stated, blocks are labeled by a pair of equals kappa and rho, say. Then this block is simple if and only if weight kappa and weight rho is 0, and not semi-simple and finite if and only if these two numbers are exactly 0 and 1. So cannot both be 0, cannot both be 1. And the infinite type if and only equal to, and both weight are 1. Yes, so this is the case that the finite type algebra tensor finite type algebra equals temp type algebra, and while otherwise. This case is easily settled. So the crucial case is the remaining case that minus capital Q is Q to S for some S between 0 and D minus 1. So let B better be the block of H and QQ labeled by this weight. And here beta is the sum of n simple roots. And we would like to know their representation type. So as blocks of Hecke algebra are symmetrical algebras, this is a well-known fact. So the theorem below reduces the problem determining the representative type to that for representatives of derived equivalence classes of blocks. So the first one was a famous result by Rickard. So let A and B two finite dimensional self-injective algebra over the field K. And if they are derived equivalent, then they are stable equivalent. And the second result is Krause's in 1997, which said, this also appeared in Chan-Chan's talk. If A and B are two finite dimensional algebra over algebra field K, and if they are stable equivalent, then they have the same representation type. So both together says that if two self-symmetrical algebras are derived equivalent, then they have the same representation type. Okay, so now I would like to apply this general result to Hecke algebras. Then for this, we may use SL2 categorification theorem by Chen and Ruquier. So recall, Chen and Ruquier proved the SL2 categorification theorem, which appeared in Annals of Math in 2008, and applied it to cyclotron Hecke algebras in the paper. So in particular, it gives derived equivalence among blocks of Hn QQ if minus Q is a power of Q. So as I wrote, let minus capital Q be Q to S, and the lambda to be the level 2 weight, lambda 0% lambda S as before, and we denote by B beta, the block of Hn QQ divided by this weight. Then, so the result of Chan-Ruquier applied here is the following. So let W be the affine symmetric group generated by SLS1 to SE minus 1. And if lambda minus gamma and lambda minus beta are in the same W orbit, then they are derived equivalent. So we'll look at the representative W orbit on the set of weights of this level 2 highest weight module, and which is a purely combinatorial problem. And we know the answer. So let lambda be as before, and we set lambda S to be 0, and for for I not equal to 0, we define two set of non-negative combination of simple roots. And then the lemma is that representatives under the Chan-Ruquier derived equivalence are be better such that beta of the following form: lambda Si plus K delta and mu Si plus K delta. So this is just a commentary thing. So we may focus on B beta, where beta are of this form, to determine representation type. But this mu, we don't have to consider mu Si case because we have the following isomorphism algebras. And for this, we switch to cyclotron Kuiper Hecke algebras. And usually, people in this audience use special parameters, special polynomials, so-called symmetric case for Qij uv. But in type A1E-1, we have an arbitrary parameter in the definition of Qij uv. So I usually denote by lambda. And so to prove this isomorphism, we use this larger class of algebras. So because and here is the definition of cyclotron Kuiper Hecke algebras. So maybe you have seen it several times in this conference. So these are idempotents, and sum up to beta. And instead of y, I use x for these polynomial generators, and for psi I, psi 1 to psi n for the braid generators. And the defining relation maybe I can omit, and then you have seen it for several times. So, and this is a dichotomic relation. Okay. So here I focus on this case because I only consider the Hecke algebra of type B. So, but in the proof I said we use more general parameters. But here, to state the result, I only use this. And then, so this is a so-called symmetric case. The terminology I also would like to use, I would not like to use because there are too many notions of symmetric algebras and symmetric Cartan matrix and symmetric Kähler algebra. All different meaning. Anyhow, we follow the people. So this is the choice, symmetric Kähler choice. Okay, and some relations maybe you know. And now we have a famous theorem of Brandon-Khrushchev, which appeared in 2009, which also appeared in Liron's talk and Louis Sutton's talk, and so we have instrumental algebra to be better to this dichotomic Kuiper-Hecke algebras. And so one advantage of working with this is that it has many natural idempotent in U. So as I wrote here, this is a standard fact that if an algebra has an idempotent and if EAE, so idempotent truncation is wide, then A itself is wide. So, but if we use standard Cox-theta generators, it's really difficult to find many idempotents using standard Cox-theta generators. But in the definition, we naturally have many idempotents. And if I choose nu to be in a clever way, then this algebra becomes very small and can determine the structure rather completely and can show that it is wild. So in this way, we can show around the beta itself is wild in many cases. And another result we use is the following lemma proposition, which also appeared in a paper by Eldon and Nakano. And proposition is the following. So let A and B be finite dimensional K algebras. And if there is the constant C and functors f from M category of finite generated A module to finite generated B modules, and the functor E in the other direction, such that for any A module M, M is a direct sum of EFM as an A module, and if this so ratio of the dimension has upper bound C, then the wildness of A implies the wildness B. So this is the general result. So now we would like to apply this to our setting of dichotomic Kuiper-Hecke algebras. And here we need the dichotomic categorification theorem proved by Khan and Kashwara. So we have induction and reduction factors for dichotomic Kuiper-Hecke algebras, which I write Fi and Ei. And then, so Khan and Kashwara result is in graded form, but for our purpose, it is not necessary to consider grading here. So I state it in ungraded form. Then the theorem is as follows. So this also appeared in Inventions of Mathematics in 2012. So let error be the scalar product of co-root alpha I and lambda minus beta. And then one of the following summaries of end functors on the category of finite dimension, finite digit around the beta module holds. So the first is if error is not negative, then this isomorphism end functors holds. And if error is not positive, then this holds. Special case for the dichotomic Hecke algebra was proven by Monica Baggiani years ago. And this is a generalization of this. And so we start with finding the borderline of the area where R lambda betas in ik coordinates. So we don't consider general beta here, but only the beta of this form. So there are two variables, I and k. So we consider I coordinates. So we write a plane and then consider which area correspond to wild blocks. And to prove that, so actually I found candidates for minimal wild thing algebras and blocks, and wanted to show that they are wild. And so for this, either we show that the nu R lambda beta nu is wild for our nu, and or more explicit computation. And here, for example, we may use the fact that this algebra is graded. So the lemma I use is the following, easy lemma. So if E is a sum of two idempotents, also to each other, and if compute the Q dimension of this subspace, and if it satisfies this condition for I, J, 1, and 2, then the quiver has two vertices 1 and 2, and CII loops, so Cij coefficient here, CI loops on the vertex I for I equal 1 and 2, and there are at least C1, 2 arrows and C2, 1 reverse arrows between 1 and 2. And so if we can compute these Q dimensions, so it is easy to get some information on the Gabriel quiver of this idempotent truncation of R lambda beta. So the lemma may be used in the following way, for example. So if there are at least two loops on one vertex and two there, then this is a statement here. If Gabriel quiver contains this or this, then the algebra is valid. Okay. And so the problem is just to choose the appropriate nu and compute the Q dimension of this space. But we may compute the graded dimensions in the lemma by the following graded dimension. This is purely combinatorial. So for k q lambda is the sum of some statics, q degree to the degree t over t standard tableau of shape lambda such that the ledge sequence is equal to nu. So, and since we were working with A1L, A1E minus 1, this basically result was due to Brandon. And we have similar results for other affine types in our paper with William Park. But here I only treat A1L, so this result goes back to Brandon's result. Anyhow, so using this, I can compute graded dimension. So now we state the strategy to determine represent type. So recall that it is enough to consider beta of this form. And we find the minimal wide one shows that they are wide by using the previous computation of this. And we show that all the others are indeed wide by using the induction and Lifton factors in the proportion. And this reduced to a simple calculation of scalar product of roots, Li, to check that they are positive. If they are positive, they satisfy the proportion by Erdmann Nakano. So we can show that the upper side of the border are all wide. And then we analyze the remaining small number of lambda betas and determine whether they are finite obtained. So the result was for if s is not equal to 0, then the result follows. So simply if I equals 0 and k equals 0, and all finite representation type, and not simple if I equal 1 and k equals 0, and optimal representation type if I equals 0 and k equals 1 and L equals 1, and otherwise. And if R round bit is finite, we may compute the logical system in the causal project explicitly by utilizing the grading, as in the lemma. So we know that if it is finite, then it is a Brouwer tree algebra whose Brouwer tree is a straight line without existential vertex. And for I s equals 0, my student Hecke has computed type in his master thesis. But before stating that, I would like to give a remark on genetic degree. So, in this case, finite type appears when I equal 1 and k equals 0. And in this case, the labels of the ordinary characters in the block are of this form, so bipartition. And for 0, m between 0 and n, etc. And the heuristic symbols are given like this. And the genetic degrees are given by the following formula. And then a node result of minor of Hecke, the title is Brouwer trees of Hecke algebras. He defined the notion of phi defect for blocks, for generic, using genetic degrees, and determine the Brouwer tree in this setting, and of course, to go from this setting to the real block setting, one is other assumptions. For example, in type A, he needed the assumption that the characteristic of the field must not divide the order of the while group. So it is much stronger assumption than our assumption that field is only of odd characteristic. And also, anyhow, and also in here, he first considered the case he considered was the Q is only a power prime, and then he shows that in that case, this number of times Scoton polynomial phi EQ divides this is constant on the block. Okay, and this is by appearing to so height zero conjecture of the corresponding final group for retype. And so now let us compare it with our setting. So now assume that E is even. So then minus 1 equal to Q to the half of E. And we'd like to choose S to be like this. So what is S? So natural guess would be this, right? I assume that equal parameter case. Equal parameter case. Okay, so this is, so then this is minus Q. So this is, minus 1 times Q. So natural guess would be this, right? But this doesn't work. This doesn't work. If we use this and compute genetic degrees, then this phi defect is not constant on the block. So correct choice is this. Then one can, at least in small examples, one can see that phi is constant. And here we can get phi defect 1 block for this special case. Okay. And also, I would like to point out that I would like to raise a question. So as I have explained, Chuan-Ruquier derivative equivalence gives the same representation type. So if one weight space, so we have we have bipartitions, and in one way to say, one block, be mu say, and consider affine Weyl group of it. And get another set of bipartitions. What we could expect is that if this is a phi defect one block, meaning that for all the bipartitions in the block, the number of times phi divides Pw over d phi is constant. Constant is 1. And then we apply affine Weyl group action. This is also very combinatorial. Then it is also this is a very purely combinatorial question. Okay? We consider a set of partitions here, bipartition, compute the phi defect. So how many times phi divides? And then we ask, so this is simply, SI lambda is lambda minus alpha I check lambda alpha I. So this actually you can easily compute. Okay? And get another set of bipartitions on the block. So then is the phi is constant on this block is one question. And another question is also one. And of course, I would like to have that the phi defect 1 should equal to my finite type, but I don't know whether it is correct or not. Okay. Anyhow, this is for only equal parameter case, and I don't expect anything for unequal parameter case. But my method has also determined a different type of block algebras for unequal case as well. So of course, my result is broader, but if we restrict on equal parameter case, we have such an interesting combinatorial question. Okay, now I go further, and so now, so as I said, my student Hecke has computed the case where lambda is 2 times lambda 0. And by shifting, so these two cover all the cases, and shifting the lambda index lambda I, and so now the result is like this. So if I equals m k equals 0, and finally if I equals 1 and k equals 0, and here I delete one case because here I state the result only for the case that Qij uv is chosen to be symmetric KLR. But Hecke and I have proven the result for arbitrary parameter lambda hidden in Qij uv. Okay? So here actually appears the degeneration phenomenon appeared here. That is, so we have a parameter lambda for A1L. KLR, Scotum KLR. And if lambda is not equal to -1 to E, then they attain. And lambda equal to -1 to E is exactly the case, the classical case that the KLR is symmetric. So we have seen a degeneration phenomenon here. So term algebra degenerate to wild one when lambda tends to -1 to L, -1 to E. Okay. And anyhow, so this is my remark that I delete one case from here, from the general result, and now wild otherwise. So as a corollary of all the story I have told, type B are completely settled, and particularly if block algebra in type B Hecke algebra is finite, then it is a Brouwer tree algebra whose Brouwer tree is a straight line with the partics. So we have prove that the repeated type of blocks of finite type under Chewan-Rieke derivative equivalence are all Bravais-Tree algebras whose Bravais-Trees are straight lines without exceptional vertex. Now, I would like to know all the other finite type blocks. And for this, I use theorem of Omatsu, a student of WADA, who wrote a master's thesis in Japanese in 2014. And the result is as follows. Asymmetric cellular algebra of finite type is a Bravais-Tree algebra whose Bravais-Tree is a straight line. It says nothing about exceptional vertex. But this is a good result. And in fact, we can weaken the assumption symmetry to be a self-injective. And this is proven in this paper. Actually, in this paper, we handled not only self-injective of finite type, but self-injective of a term representation type of polynomial growth representation type here. And we have classified a self-injective cellular algebra of term polynomial growth representation type up to multi-equivalences under the assumption that the field has odd characteristic. And for the proof, for this, for the proof, this is a bit different. But for here, we record result by Riedman and Bush that symmetric algebra finite type are multi-equivalent to one of the trivial extension algebra, rotated algebra of thinking type, or Bravais-Tree algebras, or modified Bravais-Tree algebras. So they are rather concrete, not really concrete, but we can handle at least these algebras. So they are good enough to delete these cases. And so the proof is that using various properties of cellular algebras, we eliminate these possibilities, and the remaining is this. And in fact, for this, one may avoid the use of Omatsu theorem because there are all the results by Gabriel Riedman saying that if an symmetric algebra, if an algebra is derivative equivalent to a Bravais-Tree algebra, then the algebra itself is a Bravais-Tree algebra. So then we may appeal to a result by Stefan Koenig and Chan Shi, saying that if a Bravais-Tree algebra is cellular, then it is a Bravais-Tree whose Bravais-Tree is a straight line. So of course, for this case, so we may avoid Omatsu theorem, but this has, as I said, other generalization, and so I refer to this. So, and also, the activity of the base field is odd. So then the theory to preserve under multi-equivalent. This is also a result by Stefan and Chan. Okay. So now, block of Hecke algebras are symmetric cellular algebras, so we may apply Omatsu theorem or a combination of Koenig, Shi, and Riedman. And then therefore, the blocks of finite types are Bravais-Tree algebras, and they are derivative equivalent to Bravais-Tree algebra without expansions. Now we appeal to the Rickard-Starr theorem. Okay? So Rickard-Starr theorem says that any Bravais-Tree algebra is derivative equivalent to Bravais-Tree algebra of star shape, so symmetric Nakayama algebra, actually, so such that only the center of the star can be an exceptional vertex. And the number of edges and the multiplicity of the exceptional vertex determine the derivative equivalent classes of Bravais-Tree algebras. So we know that any finite type block is derivative equivalent to a finite type block which has no exceptional vertex. And we know that both are Bravais-Tree algebras. And we know that they are straight lines. Trees are straight lines. So as a result, we know that a block of this is, if it is of finite type, then it is Bravais-Tree algebra whose Bravais-Tree is a straight line with a vertex. Then, as I said, then we can say something about this. and this is by easy computation about the length of logical filtration of pins. So this the proof is complete, and here I would like to make a remark that here we use derived equivalence, but at the end finite types are Morita equivalent, right? Only the number of simples determines the algebra. So this is a strange phenomenon, and also we saw in the great work by Chiang-Rukia about abelian defect conjecture. They are developed, but actually they proved as a Morita equivalence. Okay, so maybe Joe has something to say about proving like this in a general framework using power experiment or something, which I don't know. So thank you very much for your attention.
Do you use covering technique in your covering technique?
No, I don't use covering theory.
Yeah, I think it's really exclusive.
I suppose it's sort of surprising that you only gave all three algebras appearing for finite type. So, but you know also something about which algebras appear for tame type.
Yeah. So yeah, I'm working on that. Actually, probably. Yeah. So I have some hope to determine the tame types for blocks of Hecke algebra because sorry.
Yeah, I was wondering whether you've seen anything which is not a power graph algebra. Because power graph algebras could be
Yeah. So yes. So hope that I will report it in the near future. But here, for example, in this work, of course, term of not of polynomial growth appears, but if we restrict to polynomial growth and if we classify self-injectives of polynomial growth, and if we assume that the number of simples is greater than or equal to 5, the only possibility of cellular algebras are Brouwer graph algebras whose tree is a straight line and which has exactly 2 exception vertices, and their matrices are exactly 2. But if the number is smaller than 5, there are other exceptions, and we have classified them in the paper.